With the rise of artificial intelligence, the fourth industrial revolution is finally upon us, generating numerous technological advancements in medicine, finance, education, and especially sustainability practices. But like every other great piece of technology, there are downsides. Developing AI models is a costly practice that involves maintaining data centers that consume large amounts of electricity, and manufacturing processing chips or data mining through energy intensive practices that produce harmful waste products. These negative externalities are noticeably hazardous for the environment in the short run, but we must also consider how AI models can be used to enhance our sustainability practices in the long run through energy forecasting, systems for optimizing energy efficiency, and models for tracking energy accessibility.
So, what are the pros and cons of AI? Some of the pros are AI can help optimize energy efficiency, can help improve energy forecasting for renewable energy, and it can make energy more accessible. Some of the cons are there's not much information about energy usage, and AI relies heavily on traditional energy sources currently. And lastly, energy efficiency just simply can't improve forever. AI and training different AI and machine learning models can be very energy intensive. For example, training one natural language processing model emits 300,000 kilograms of carbon, which is 5 times the average carbon emissions from a car's lifespan. This is a large quantity of carbon emissions, especially considering all that energy to train just one model. To get a better understanding of the overall impact of AI, we can look at the overall energy usage from data centers. So energy usage of data centers increased from 153 terawatt hours to 203 terawatt hours from 2005 to 2010. In 2018, energy centers used 205 terawatt hours of energy, and compute instances increased by 550% from 2010 to 2018. We see that over time, the amount of energy used has plateaued despite the number of compute instances increasing so drastically. This is due to significant improvements in energy efficiency. We can see on the chart that as service demand has increased with more data center traffic and workloads, the energy efficiency has also increased to match the demand without a significant increase in energy usage. In fact, the increased demand paired with the stable energy usage means that the energy intensity, or the energy used per compute instance, decreased by 20% annually from 2010 to 2018. So, do the energy efficiency improvements mean that AI is the future? Well, that depends on whether or not these improvements in efficiency will continue as demand continues to increase. At least in the short term, the energy efficiency advancements made so far are expected to be able to handle the increase in demand. As you can see on the chart, the predicted energy usage stays around 200 terawatt hours per year, even with a double demand of compute instances. However, beyond the short term, it is unclear on what energy usage will look like. It is likely that energy efficiency advancements will eventually slow down, so to ensure that carbon emissions don't spike, there needs to be a shift to cleaner energy sources. Today, the energy that is used by data centers is still coming from more traditional sources like coal plants or other fossil fuel-based plants. Companies like Google and Amazon have made pledges to have net zero carbon emissions by 2040. However, many of their actions do not seem to support their pledges. For example, in 2019, Amazon's greenhouse emissions increased by 15% from 2018. While this increase may have been due to an increase in sales, it is still alarming that despite their pledges, they are still increasing carbon emissions. There is also the use of the Equinix DC2 data center in Virginia. This data center is the top data center in the United States, so it's without saying that it uses vast amounts of energy in order to function. Most of the energy used by this data center comes from fossil fuels, as only 1% of Virginia's energy comes from renewable energy sources. So, despite claims and pledges made by companies, they're still heavily relying on fossil fuels for their energy. The major problem with AI in terms of its impact on the environment is the lack of publicly available data about how much energy is being used and where it's coming from. Most of the information we have about emissions and energy use of these companies are estimates because the companies are reticent to share information about their energy use and their energy mix. In order for improvements to be made, it is critical that the data is made public so research can be done and regulation can be put in place to ensure that the negative environmental impact of AI can be mitigated.
Despite leading to some short term costs, artificial intelligence is likely to revolutionize future sustainability practices in three major ways: optimizing energy efficiency, improving energy forecasting, and making energy more accessible. AI models are useful in improving energy usage by developing models to help energy systems adapt to dynamic environments. Let us consider Google's data centers. As mentioned before, data centers require constant cooling. However, predicting redistributions of energy for cooling can be difficult due to the variability in operating conditions that we see in data centers. To combat this problem, we can produce a power usage effectiveness model, which takes historical data about the data center or energy system and generates layers of deep neural networks, which creates various cases and scenarios that account for factors like temperature, pressure, and energy overheads. Please note that deep neural networks are essentially a branch of AI models that are able to take a data set and decide for itself which features or variables to analyze, which mimics how the human brain works. This model resulted in a 40% reduction of cooling in Google's data centers and an overall 15% improvement in energy efficiency. These models can be used to negate the cost caused by AI models, as energy savings will increase exponentially with more historical data. Energy forecasting also uses historical data to improve the operating conditions of an energy system, but in a different way. Here, historical data predicts optimal conditions for energy harvesting. Renewable energy sources like wind and solar energy are dependent on environmental conditions, making them unpredictable at times. When energy availability is capped during certain times due to changing weather patterns, it can be costly to schedule energy production from reserve plants. However, by developing an AI model that synthesizes historical weather data from satellites and ground sensor networks, we can predict weather conditions up to 48 hours ahead of time. The Sunshot Initiative found that solar forecasting was improved by 30% due to integrating deep learning models. In addition, a 2020 IEEE study by the University of Electronics, Science and Technology of China found another use for solar forecasting. By using neural networks to predict the sun's position during the day, they were able to adjust the angling of solar panels and increase energy collection by 32%. Finally, AI models can significantly improve the demand-side management of energy production plants by monitoring consumption habits of consumers and creating consumption patterns for each consumer. This is also done to some degree in homes through the use of smart meters. The AI models can also make suggestions to customers to lower energy consumption. These changes can significantly reduce a customer's utility bill by 40%, according to a French energy startup called BeByte. This system can eventually reduce energy pricing for consumers and identify areas for redistributions of power, which will make energy more affordable and accessible. Due to this application of demand-side management AI models, the average electricity costs of renewable energy sources are expected to drop significantly from 12 cents per kilowatt hour to 7 cents per kilowatt hour by 2030. As seen in this supply and demand diagram, the supply line is expected to decrease thanks to a reduction in the operating costs of energy production, thereby reducing the price of electricity for consumers from 12 to 7 cents. This could very well lead to energy conversion initiatives from fossil fuel energy sources to renewable energy sources, as the prices of renewable energy sources will now be competitive with that of fossil fuel energy sources. AI models may harbor several environmental costs in the short run, but these costs may very well be worth it to achieve more sustainable energy production in the future. AI models do present short-term consequences in the form of high energy consumption, production of hazardous materials, and limitations imposed by data collection, but the long-run benefits of AI models in energy production can fundamentally change the energy game for producers and consumers by improving energy efficiency, cost, and distribution. These elements can potentially alleviate the short-term costs imposed by AI models. AI models are also significant to other economic sectors like healthcare, finance, and education. In the end, whether or not AI is a path forward depends on our ability to innovate and improve upon the technology we have today. We need to ensure that energy efficiency continues to improve, as well as making a more mainstream switch towards cleaner energies. However, with the help of AI, this seems possible, and so there is optimism about the potential applications of AI in the future.